Once again, welcome to another session. And last time we were dealing with the Millman's theorem. Today we are going to start on maximum power transfer. And always, whatever I have always advice is that first know what the theorem states. That from that statement, you can always develop the depth of the knowledge from the statement that forms the basis of reasoning. So first we state the theorem. It states that maximum power is transferred from the source to the load if the load impedance is made equal to the internal resistance of the source. Internal resistance of the source, and all the EMF sources and all the EMF sources being replaced by their internal resistances. So this is basically what the maximum theorem dictates. So from this, we shall just do the analysis of this by just using an example of a circuit. So consider the circuit shown below. So we shall draw a circuit here. So this example of a circuit that we have, so this RTH can also be abbreviated as RI as internal resistance. This circuit now refers to whatever we are going to analyze, and we normally say that for maximum power transfer, then the resistance of the load and the load impedance must be equal to the internal resistance. And in this case, internal resistance is abbreviated by Thevenin's internal resistance or Norton internal resistance, with the source being the voltage, because we are talking about RTH or the internal resistance as RTH, then the source must be VTH. If you are talking about the Norton as the internal resistance, then the source will be the short circuit current. So this is basically what we shall dwell on. So for us to have this power, that means that power is normally given by power transferred to the load. Power transferred to the load. Power is only given by I squared R. R of L. The R of L. But when you look at this, for us to get I must be equal to VTH over R of TH plus R of L. That is I, which is equivalent to VTH R of I plus R of L. That's what gives us current. So for us to derive, for us now, power is then given by, power is given by I squared R of L. It's supposed to be VTH over R of I plus R of L. This now is squared multiplied by R of L. So this is basically having generated, if you just replace the value of current, then we shall be able to differentiate that. So this is the basic analogy that we're going to be using. And for maximum power, then it means that we must differentiate this with respect to the load RL. So for us to get the maximum power is determined, maximum power is determined by differentiating the above equation with respect to the load RL. So we get dP d of RL. So we get this means that we shall get d RL of the entire equation VTH over R of I plus R of L squared multiplied by R of L. That's the equation that we're going to get. And we realize that when differentiating this, there's something that we call about the quotient. It's about the quotient. The division, the differentiation of a dividing number, and there's an RL, yeah, but the VTH is a constant which can be taken as out. So that means we shall have this being equal to VTH being taken as out. Then we differentiate the remaining as DRL. We have the DRL. Then have the RL. Down here we have RI plus RL. This is what all squared. So that's what we're going to be differentiating, which is supposed to give us VTH into RI plus RL minus 2. Reduce minus 2. We hold this, then differentiate this, so it's 1. We are holding the denominator, differentiating this. If you differentiate the RL with respect to DRL, you get R1, 1 multiplied by that, minus 2. We differentiate this, 2 into RI plus RL. The power reduces to 1. The power reduces to 1. Then we multiply by R of L, because R of L is what we are holding as constant. We have finished differentiating that. And the denominator now goes to square. We are holding that. This now is supposed to be RI plus RL square. This is what is equated to 0. So that we get the maximum power. And remember, anytime we differentiate, when we differentiate, get the peak value of any expression. So this is what we equate to 0. This is what we equate to 0. Then we are able to equate it this way. When we equate that, we shall have it. We shall have. Then when we equate that, we are going to be equating VTH equals multiply then VTH squared into RI Ri plus R of L squared minus 2 Ri plus RL dot RL is supposed to be equals to 0. If you cross multiply, you're going to get equal to 0. Eh? And this is what we refer to as dP dRL. So by default, we have, if VTH is 0, then the entire this is 0. If VTH is equals to 0 as maximum, then Ri plus RL squared is equated to be 0. So we don't proceed with it. But minus 2 into Ri plus RL dot RL is equals to 0. That means that RL can be equals to 0, which is not a reality. So RL cannot be equals to 0. Then if you open this, you'll have minus 2 Ri plus RL plus 2 RL is supposed to be 0. Then 2R of I minus 2R of I is supposed to be minus 2R of L. So minus and minus cancels. And in this case, we shall have R of I is equals to R of L. And this gives us the true equation for maximum power transfer. So this is the condition that we need to be able to understand. How do we get here? We first differentiate the power equation. And when we get to this point here, either this is equals to 0 or the entire this is equals to 0. That's exactly what we mean. So by doing this, we shall be able to come up with this condition for us to get the required, or to prove that this is the maximum formula that's required. So from this case, you're going to understand about the maximum power transferred. The maximum power transferred from the formula there that we applied. We recall that power is supposed to be VTH over R of I plus R of L. This is squared multiplied by R of L. But if this is the condition, then we shall have power as VTH squared. R of I plus R of L, it will be 2 R of L squared multiplied by R of L. 2 R of VTH, 2 of RL squared multiplied by R of L. We shall have VTH over 4 R of L squared multiplied by R of L. Then power is supposed to be given by VTH squared over 4 RL. So this condition must also be able to arrive at. So this is our first example, and in this example, the source voltage, the source to the circuit, the energizer is 120 volts. So anytime you are given a maximum power transfer circuit with a voltage as a source, you must be able to determine the Thevenin's voltage, and that one will act as the source, and the internal resistance is going to be the Thevenin's internal resistance. So first when the load is removed, then we shall have our ITH, our I being equals to, with the load removed. So with the load removed, I is supposed to be 120 over 40 plus 20, which becomes 120 over 60, supposed to be 2 amps. So Thevenin's voltage, VTH is supposed to be I of R. Then I of R shall be able to multiply by the resistor in parallel. In parallel, 20 ohms. 20 ohms. This 2 ohms multiplied by 20 ohms. This is supposed to be 40 volts. This is the VTH. Then from there we turn the Thevenin's internal resistance. Thevenin's internal resistance. Thevenin's internal resistance is determined from this circuit. We now draw the circuit. So this is 60 ohms. This is 20 ohms. This is 40 ohms. Looking in, then shall have RTH being equals to 60 plus 40 times 20 over 40 plus 20, which gives us 73.33 ohms. So that's the Thevenin's internal resistance. This is what is also equals to R of I, this equals to R of TH. So for maximum power to be transferred, that means that our load RL must be equals to RTH. So in our formula now, we are going to replace RTH with R of I, which is equals to R of load. So we are going to draw the circuit so that we are able to know what the maximum power transfer is. Then determining now the power, determining the power delivered to the load. Then for maximum power, R of I is equals to R of L is equals to R of TH. Then power is supposed to be VTH squared over 4 R of L. VTH, we have it in our formula there as 40 volts squared over 4. RL is 73.33. Then we get to our maximum power as 5.45 watts. So once again, let us proceed with the second example and this example too. And anytime you are given a circuit with the current as a source, whatever you need to understand is that we need to use now the Norton's theorem or the Norton's approach as the value for us to be able to determine that. So the first thing, determine the short circuit current, which is going to act as our source. So the short circuit current, I of SC. The short circuit is put across the load, I of SC. If you put a short circuit across the load here, so that we have the short circuit at this point, I of SC. I of SC is supposed to be 300 over 300 plus 300 multiplied by 1 amp. And this becomes 0.5 amps. So from there, we determine the Norton's internal resistance. R of N is supposed to be R of N, we now determine the Norton's internal resistance. Internal resistance, R of N. R of N, in this case, the circuit is going to appear this way. Looking in. So R of n therefore means that will be 600 times 600 over 600 plus 3 plus 600. This 600 is because we are looking in the two resistors are in series in parallel with this 600. So we shall have 600 times 600 over 600 plus 600, not 300. 600. We take our calculator. That is 610 divided by 12. We shall have our answers as 300 ohms, Rn as 300 ohms. So for maximum power transfer, Rn is supposed to be R of L. It's going to be 300 ohms. So we have our circuit drawn this way. This becomes our I of SC. This becomes our R of N, which is 300 ohms. And this becomes our RL now, which is the variable across the terminals AB as 300 ohms. So power is supposed to be I squared R and the RL. So I suppose, given the two resistors are equal, we shall just half the source. So this half of that, half of 0.5 is 0.25. This is what shall be squared multiplied by 300 ohms. We take our calculator. This now becomes 8.75 watts. So that is the answer and the final solution to that example. So from there we shall talk about the conditions for maximum power transfer. Conditions for maximum power transfer. Conditions for maximum power transfer. One of the things, so one thing must to assume, proceed. One thing must be able to give a condition is that anytime you are seeing this, you must assume that we are using the impedance. And also, when the load is purely resistive or at resonance, we talk about the load of purely resistive. And then the first condition we will put here is the maximum power transferred. The maximum power is transferred to the load if the load resistance, resistance RL is made equal to the impedance of the source circuit. In this case, RL is supposed to be the root of R squared plus X squared. Which must also be equal to R of I, where R is the internal resistance and X is the internal, is the reactance of the circuit. And number 2, the condition number 2 is that we are assuming that the load is variable and also the internal resistance is variable. So when the load of the source impedance is variable, when the load of the source impedance is, when the load of the source impedance is variable, then maximum power is transferred. The maximum power is transferred if the load resistance, if the load resistance is made equal to the variable, if the load resistance is made equal to the variable resistance, then in this case we shall have R plus Jx is equals to R plus Jx. In this case is that the small r and the small x refers to them as internal. In this case, we are going for a variable load and the internal resistance that keeps on varying the imaginary value. And the same way, we shall also replace the internal resistance with a reactance that is also variable. Condition number 3. When the load and the load resistance and the reactance are both independently variable. When both the load resistance and reactance are independently variable and adjustable. Variable and adjustable. Maximum power is transferred. Maximum power is transferred when our x equals to minus x and our r equals to minus r. So by doing this, we shall be able to get the condition for that. So these are the conditions for maximum power transfer, and this makes it us to understand what we need to put on in practice for us to be able to ensure that in amplifiers the power is given maximally to the load. JEMSHAH.